We're going to find all the complex zeros of this cubic polynomial. This is a degree 3 polynomial, so that means there will be exactly 3 complex zeros. To start off, we would try factoring. To start off, we need to set this equal to 0 first. And then we're trying to solve this equation. Now, since there are 4 terms, I may try factoring to begin. I could try factor by grouping. So if I group together the first 2 and the second 2, and then take out the greatest common factor in each one, greatest common factor in this first one is x squared, which would leave an x minus 1 on the inside. Greatest common factor in the second one is just a 1, so that would leave the inside unchanged. For factor by grouping to work, these 2 things that are in parentheses now have to be identical. And I can see from this one that they're not. So I know grouping is not going to work for me on this one. So now I have to try something else. So another way that I could go about trying to find the zeros is I could use the possible rational zero theorem. To get an idea of zeros that I should try. So this is going to be plus or minus all of the factors of the constant. The constant in this one is 17. So all your factors of 17 are just 1 and 17 because it's a prime number. Divided by all of the factors of your lead coefficient. The lead coefficient in this one is just a 1. So the only numbers I should bother trying would be a positive or negative 1 or positive or negative 17. So I'm going to start with a positive 1. I'm using synthetic division to test this polynomial to see if it is actually divisible by the factor x minus 1. So I put a positive 1 there, and then I write down just the coefficients. Bring down the first term and multiply, and add, multiply, add, multiply, and add. If 1 is a 0 of this polynomial, then I would have to have gotten a 0 as the remainder in this last position here. So I can rule out 1. I know 1 is not going to be one of my zeros. So next I'll try negative 1. So I bring down the 1, multiply, add, multiply, add, multiply, and add. This time I got 0 as a remainder, so that means that this negative 1 is actually one of my zeros. So I'm going to go ahead and write that down as part of my answer. Up here at the top, I'm going to say the zeros are, and I'm going to list them. So negative 1 is one that I found. I know that there are 2 more because this is a cubic polynomial, which means there are exactly 3 complex zeros. So I still need 2 more, so I know I need to continue trying to solve. Now, a nice thing about this synthetic division is once I've performed the synthetic division once, I now have a new polynomial to work with here. I've got this one here, and the degree of this polynomial is going to be 1 less than the degree of the one that I started with. This one was a degree 3, so that means this will be a degree 2 polynomial. So I'm going to turn that back into its polynomial form. That'd be x squared, 1x squared, minus 2x, plus 17. And I'll set that equal to 0 to solve it. Now, in order to solve this one, again, I would start by trying factoring, but I exhaust the list of factors of 17 pretty quickly. That's only 1 and 17, and there's no way I can get those to add to make a negative 2. So I'm going to use complete the square instead. So for complete the square, I'm grouping together the x squared and the x term and leaving a space inside the parentheses. In that space, I'm going to add in b divided by 2 squared. So that's negative 2 divided by 2 squared. Negative 2 divided by 2 is negative 1. negative 1 squared is 1. So I'm going to add 1 in here. And whatever I add on the inside, I have to then subtract on the outside so that I'm keeping this equation the same as it was originally. This creates a trinomial here that can be factored. And in fact, it factors into a perfect square. It factors into x minus 1 squared. A plus 17 minus 1 can be simplified into a plus 16. Now I'm going to solve this equation by pulling away everything that's happening to the x a piece at a time, starting with the outermost thing. So I'm going to be moving this 16 to the other side of the equation by subtracting it. Now I need to undo this square, and the way to do that, of course, is taking a square root. So I'll take the square root of both sides of the equation, remembering to put in a plus or minus sign on the right side. On the left, the square and the square root cancel each other out, leaving just x minus 1. On the right, I have plus or minus the square root of a negative 16. The square root of negative 16 is 4i. Now to continue solving for x, I would still need to add 1 to both sides of this equation. Now since 1 is a real number, and this positive and negative 4i are imaginary numbers, I can't actually combine them when I add the 1 to this side. So I'm just going to write it in front. 1 plus or minus 4i. This gives me 2 additional complex zeros. These are the imaginary ones. So I'm going to write these down as part of my solution, going back up to the top, and putting it back with my answers up here. So 1 plus 4i is one of those zeros, and 1 minus 4i is the other. This is how you find the complex zeros. They cannot be found by factoring alone. You do actually have to take your quadratic and set it equal to 0 at some point and solve it using some other method.